Alright, so far we have seen that the human visual system responds with these three responses R1, R2, R3 to some light source. And yeah, we have built everything around that concept actually. But there's more to be said about color, and that's the first part that we will now talk about, color constancy. And after that, we will say a bit more about how we can quantify color and not be too sensitive to different environmental factors. But first, color constancy. So what do we mean by that? Let's revisit this Benusa ring. We saw it with different intensities. This is basically the same setup, but now with different colors. And we will change this pattern only so slightly by adding two small horizontal lines, like that. And you start to see, although less outspoken than with intensities, that now the upper part of the ring and the lower part of the ring have different colors. So it would look a little bit more yellowish here, maybe a bit more reddish on the top. So you get these different color perceptions. Just by adding these two lines, that's the only thing that changed. Let's look at a more outspoken example of what we have just seen, which is all about context. Right? The Benusa ring, we mentioned that with intensity. It was about context of the background versus the foreground. That is different for the top and the bottom. But it's a better example to show color constancy. So suppose we have this scene here, go with hat in white illumination. And this is the same scene, but now under very greenish illumination. And first of all, note that you can immediately see that, yeah, the overall illumination is greenish here, right? So as a human, you immediately see that. But also note that this hat here still looks like red to us, although there is objectively no red to be seen, because there are no wavelengths from the red part of the spectrum falling onto the scene and being reflected towards us. So now let's focus on two parts of this scene. We'll select part of the hat, and we'll select part of this background here. Notice that this background we did change. Here it's greenish, and here it's also reddish. So this is a small manipulation. And you will see the reason very soon. So let's look at these patches. Here they are. So this is the patch on the hat, and that's the background. Notice something remarkable here. We see that these two colors could not be more different. Yet, in both cases, originally, in the original scene, with full visibility of all the parts, would have said, oh, that's red. Maybe no longer here, but this we also called red. For us, that was more reddish. Whereas the background seemed to change color between the two parts, but actually, objectively, the color is exactly the same. Going back to the original. Here we can see this is red, but actually, objectively, it's green. Here the background seems to be different. This seems to be red, that seems to be green. Objectively, the color has not changed at all. And that implies there's much more going on in the brain when we handle color than a local response. Right? So these responses are very local, but then there's further processing that involves the entire environment of those patches, and that has a lot of influence as well. So there's more to color perception than three primaries after all, than three responses after all. So two things we could see here. Patches keep their color appearance even if they reflect differently, like on the hat. In one case it was actually red, yeah, in the other case it was in fact green, but both we called red. And patches change their color appearance, but in fact, they reflect identically. That was the background. Two identical patches, but they look different to us in terms of their color. And of course, only explicable when you drag in the environment. So indeed, there's much more to color perception than just 3 responses of the 3 cone types. This whole idea of color constancy and the fact that humans can actually see color even under differently colored illuminations has been studied extensively by Edwin Land in psychophysics. And he also had the Retinex theory and so on, about how that could go on computationally. Now, it's kind of intriguing what's going on here if you come to think about it. So we have seen this figure before. So we get on our camera system, in fact, a combined effect of, on the one hand, the color of the light source. So the light source has a certain spectral composition. The light falls onto a surface, and in certain parts of the spectrum are reflected more or less by that surface. So it's multiplied here it is by this reflectance, and it's that product that we see. We see the product of the presence of certain wavelengths and how much of these wavelengths are being reflected towards the camera. It's that product that we see at every place. So there are these 2 components, and humans can disentangle these 2 very well. We can actually see, oh, the color of the illuminant was green, go with hat, right? But the actual color of the surface was still red. Objectively, there was no red to be reflected. Yet we could see red because of this more intricate processing that goes on in the brain. So we see this product, and we can see the 2 components, 2 factors in that product. Yeah, this is, by the way, a trick you could use if you have a spectral reflection. These are places where the surface acts as a mirror, and you see the pure color of the illuminant. But it's not like human vision really needs that trick. So we don't need any specularity in scenes to do that disentanglement. We can do it in any kind of scene almost. Okay. So color constancy, of course, is very interesting, because if you want to say something about objects, we don't want the illuminant to talk into the decision too much. We want to know what the real property of the surface of the object is. The real reflectance, that is what we are often after. And one must not underestimate how even natural light, because you may say, yeah, but natural light is all white, right? Well, sunlight in the morning, at noon, in the evening, it's pretty different. And we have already spoken about longer wavelengths reaching us more at dusk and dawn, for instance. So the color of the illuminant, even if it's the sun, will change. So it will be very useful if we can peel that factor out of our analysis and just study the actual color of the surface, the real reflectance characteristics of a surface. Now with deep learning, people are getting closer to that. We are not there quite yet, but recent advances have been made. But in general, it's a hard problem. And several attempts have been made to do the same computationally with more or less success. What we will discuss here is not really a color constancy algorithm, but we will look at color features or features that are related to color and are less sensitive to that kind of environmental changes that you just saw. But these are not really color constant features that we will extract, but something a bit in that direction, less variable if you change, for instance, the color of the illuminant. That's why I called it a Pullman version of color constancy before. So, extracting the true surface color under varying illumination, as the human visual system can, is very difficult. We can't do it really. So we go for a less ambitious goal, and we want to extract color features that do not change with the illumination. In fact, we will look at 3 cases. We will look at a change of color of the illuminant. We call that an internal change here. So that's a spectral change of the illuminant. Secondly, we'll look at the case where we move around with the light source. So we reposition the light source, which also has an effect, of course, of how much is being reflected towards the camera. And also in nature, of course, that is bound to happen as the sun moves across the heavens. And finally, we have the combination of the two, spectral and geometric changes together, both of them. Here the first case, a spectral change of the illuminant. So the color of the illuminant will change, but we keep it fixed to the same position. To clarify the drawing a bit, so here suppose that's a surface that will reflect the light towards us. Here we have the illuminant, the color of the illuminant being yellow in this case, and we are observing this scene from this camera here, from this position. So that's the initial situation. And then we change the color of the illuminant. So now we shine light of a different color onto the surface. That light will get reflected, and of course there will be changes because we get now a different mix of wavelengths falling onto the surface. Now mathematically, it's a bit simplified model maybe, but mathematically we can say that if you have changed the spectral composition of the light source, what will happen is, in terms of what we get back in the camera, that we get now, compared to the original, the yellow light, let's say we got, under the yellowish light, we got this IR, RG, RIB for 3 colors in the color camera. That's the response we got. And now we get different amounts. I prime for red, for green, and for blue, being alpha times IR, beta times IG, and gamma times IB. So different relative amounts, because the color has changed. We have now much more red than before. So we have these different alphas, the alpha, beta, and gammas to model that change. Now we want to get out something color related, but without suffering from that change, because if we just get the output of a camera, the RGB values, we would get changes on it, with alpha, with beta, with gamma, and so on. If we have a classifier, depending on these 3 spectral bands, the classifier may be negatively impacted by that change quite a bit. So, but what we can do is to look at 2 different points now. And if we have then a change of spectral composition of the light source, we can make it disappear. For instance, if we have the 2 red channels at these 2 points, and we take the ratio of the red channels at these 2 points. So after the change of color of the illuminant, we have these prime values here, which are alpha, the original red 4.1, and alpha times the original red 4.2. But you see that ratio will make sure that alpha cancels out, and we are back at the original ratio, the original value. So it is as if nothing happened, even if the color of the illuminant has changed. The price we pay, of course, is we have now to use these 2 different points. And by the way, if you have a gamma different from 1, that doesn't matter much, the same story. So if you have a gamma value for your camera that is not nicely 1, as most modern cameras almost have, then the whole thing would still be valid. Okay, but now the second change, the geometric change. So now we will start moving things around. The color of the illuminant will not be changed, but the position of the illuminant and the camera we allow them all to change, to go, for instance, to that new situation. Okay. What is now the consequence is that the amount of light reflected towards us, because of this new geometry, will be different. So we have the same kind of additional reflectance or lesser reflectance in all the spectral bands. So if you now look at a certain point on the surface, this is just position of the point on the surface, so you have coordinates x and y on that surface, there is a factor, S, that has to be applied to all spectral bands, in the same degree, to cater for a change of geometry, that additional or lesser reflection towards the camera. So the new RGB values, so to speak, the responses for the three colors, is the old, but multiplied with this factor, which could be smaller than 1 or larger than 1, but it's the same for the three bands. That's the important thing here. So what we can do now, if you want to eliminate sensitivity to geometric changes, is to look at ratios again, but for different spectral bands. So for instance, you can use red and green, you take the ratio, that will be the new value, well, it's the same as the old value. And the same here, if you take a ratio from red and blue, it's again the same. So these are invariants that are color-based. So the question then is, yes, often of course you will have the two effects. The color will change and the geometry. You move around with a camera in the world, you start at 9 o'clock in the morning and then it becomes 1 in the afternoon. The sun is at a different position, you have moved in the meantime, and the color is also different for the illuminance because of the time of day. Can we still get features that are based on color responses that have not changed under this combination of spectral and geometric modifications? Well, yes, we can. So that will be like the new position, right? So you see now both color and positions have changed. So what we will do is to take this double ratio. So we combine the two tricks that we just saw. We have 2 points, point 1, point 2, and we have 2 color bands, in this case red and green. And if we then take that particular double ratio, you see that all the factors that we have discussed earlier will indeed cancel out, and you have back the original value. And you can again look at what happens if you have different gammas and so on. It in fact doesn't matter. That we won't discuss. One final word maybe about reflection here. Because that is the holy grail where people are now also working towards to get. It's called the BRDF, the bidirectional reflection distribution function, and this for different wavelengths. So what is the problem here? So the idea is that if you have a patch on the surface and you have a normal, and you come in on a certain angle here, then you want to know how much is being reflected in different directions. So, but for all incoming angles, this blue vector, any direction, you want to know for each of these directions what happens in terms of reflection in all the directions of that red angle. So you want to have any blue angle or any incoming blue vector, any outgoing red vector in relative positions, and be able to answer from the light that comes in how much is getting reflected, and that also for each of the wavelengths. Now most surfaces behave nicely in a sense that it's all pretty wavelength independent. So the amount of reflection doesn't depend too much on the wavelength. But there are exceptions. If you think of mother of pearl, for instance, it's a very typical example where it's not true. And these are of course very intriguing surfaces because the color seems to change as you move around, so intriguing to people. But for most surfaces in reality, this function is based on 4 dimensions, incoming angle, outgoing angle, all the combinations thereof, is not too dependent on the wavelength. So you can leave the wavelength out of consideration in many cases, but not always. And that's a 4-dimensional function to measure. Very difficult to measure in practice, but that's like the optimal characterization of reflectance. I just want to make a note of that, to mention BRDF as a concept so that you know what it refers to. It's a 4D function specifying the radiance for an outgoing direction given an irradiance for an incoming direction relative to the normal and ideally for one wavelength at a time, but as I said, often not quite so dependent on the wavelength so that you don't have to care too much about that part. But 4-dimensional. This is a specification for the different angles here. You see the definitions down here. So it's a 4-dimensional function. And this is an example of a device that is used to measure such a function. It's a hemispherical setup with multiple lights. So you can shine lights on the different incoming directions and then start to estimate how much of the light gets back to you. So this is a hemisphere. On the inside are LEDs that will illuminate the surface. The object is placed in the middle here, and then the camera is looking down. So notice, for a real BRDF measurement, you would have to measure the camera around as well and do the measurement for all the different LEDs being activated, all different directions of incoming light. In this case, we only have a single direction of observation, but you can infer quite a bit from that already. So and here you see an estimation of the normals of that surface based on that analysis. But enough of that. This is more about 3D. We see that later. And here is now a computer model of this tiger moth. And the focus is on getting a precise replica of the different colors as the light source moves about. So what you will see here is a light source being moved about. We don't change the position of the camera, but we want to mimic how the shading and the colors change as the light source is moved, as the illumination is coming from a different direction. And this, as I mentioned, is only a subproblem of measuring a BRDF, because then you would also want to know, for a full BRDF, what happens if you change the viewing position as well. That's not even answered here. Okay. Here you move this virtual light, you see the decoloration, the lower wings going from yellowish to brownish, color changes happening based on the measurements for different incoming angles and then making a mathematical model out of that. Here a summary. So this is reality, and this is the simulated version as comes out from the mathematical model of the surface reflectance characteristics. For different directions of illumination, between the two rows, different illuminations here and here, and you see that the model captures the reality pretty well. But that is not even taking into account changing viewing direction, as I mentioned. That would have to be included as well for real BRDF. And we are working on that.